Okay, great.
So next talk will be given by Agranat-Tamir about combinatorics of time-consistent Gal trees. You can go.
Okay, so thank you. I'd like to thank the organizers for the opportunity, especially to speak online. I apologize for not being there. So this is work performed with my advisor, Noah Rosenberg, and with Bernard Gittenberger and with Michael Fuchs. Okay. So evolutionary processes have long been described using rooted binary trees, where they describe speciation, which is what we see here. And they can describe divergence of populations, evolution of genes, but not all evolutionary processes can be described by divergence due to drift or mutation. Some processes also involve hybridization, so that in the past few years, there's been a surge in the number of studies about phylogenetic networks rather than just phylogenetic trees. So I will now give a definition for rooted binary phylogenetic network, in short, just phylogenetic network. And I'm going to follow throughout the entire talk here the definitions by Kong et al. 2022. So a phylogenetic network is directed here from the top to bottom. It has a root with in degree 0 and out degree 2, tree nodes with in degree 1 and out degree 2, reticulation nodes which make it a network with in degree 2 and out degree 1, and leaves with in degree 1 and out degree 0. My talk will be here about non-plane leaf labeled networks, where the leaves are labeled by either extant species, populations, and so on. And the network describes the process by which they evolve from their common ancestor, the root. Now, another definition I'm going to use is that of a reticulation cycle, which is a pair of directed paths with a common start and common end, but otherwise which are disjoint. So, for example, this is a reticulation cycle. So we have the start and the end, and these two pathways are otherwise disjoint. So in my talk, I'm going to give an overview of main classes of phylogenetic networks which have been studied in the past few years. I will show our results on one such type of networks, the time-consistent gold trees. I will compare this to results on other phylogenetic networks, which all of these results will be asymptotic approximations. And in the end, I will also give exact number of small time-consistent gold trees. So I will now give an overview of some of these types of phylogenetic networks, which are a bit more specific than just the general one, which I just defined. So here I will give a diagram with the subset relation, so that we have that this type of phylogenetic network is contained within this type of phylogenetic network. So first, we go to the reticulation visible network, which is a phylogenetic network with the additional property that for each the reticulation node is visible. That is, there is a leaf whereby all the paths from the root to the leaf must pass the reticulation node. So for example, this is a reticulation node, and this is a leaf where all the paths from the root to the leaf pass through this reticulation node. On the other hand, in general phylogenetic networks, this is not necessarily the case, as we see in this light blue node, which is a reticulation node, which is not visible. A very popular type of phylogenetic networks are tree-child networks, which are phylogenetic networks with the additional property that each non-leaf node has a child, which is a tree node. So for example, we have this node, and this child is a tree node. In, for example, this reticulation visible network, it is not a tree-child network because both children of this light blue node are reticulation nodes. Because we're looking at these networks usually with a biological context, then many times people look at what they call normal networks, which are just tree-child networks with no shortcuts. So a shortcut is usually, it involves the reticulation node and the edges with the reticulation node, and we see that in this case, these are no shortcuts. On the other hand, in a general three-child network, we can have a shortcut, which is this one. And biologically speaking, it is less likely because what we have is that these two, this node and this node, are the parents of this node, whereas they themselves have an ancestor-descendant relation. Another popular type of phylogenetic network are gold networks. And these are phylogenetic networks with the additional property that each reticulation node is present in exactly one reticulation cycle. So for example, this node is present in only one reticulation cycle, and they are distinct from three-child networks. So for example, if we look at this light blue node, its two children are reticulation nodes, so this is not a three-child network. And vice versa, if we look at this three-child network, then we find that this reticulation node is present in two reticulation cycles. So they're distinct from one another, and this is why people also look at the intersection between these two types of phylogenetic networks at the gold three-child networks. And the simplest type of phylogenetic networks are gold trees, and they are just phylogenetic networks where every node is present in at most one reticulation cycle. And we see that these other types of networks are not gold trees. We see here these nodes appear in two reticulation cycles and these one as well. The networks we've been working on are time-consistent gold trees, again, because we like to look at them in a biological context, evolutionary context. So these are gold trees where what we want is that the two parents and the reticulation node all coexist, and we like to represent this on a horizontal line. So we have these two parents and their child, the reticulation node, all present at the same time. And this happens in all the golds and in all of these reticulation cycles, and they're called golds. In gold tree, we call the reticulation cycle, we call it a gold. This is just because on some trees we have this kind of growth of kind of balls, which are called golds, and this is just taking them to this graphs. And again, in a general gold tree, it's not necessarily the case. We see here in this gold, we see that we have two parents and the child, and they don't coexist at the same time. Okay, so now I'm going to show you some results, other results not performed by me. So again, we just look at this diagram of the different relations between just these types of phylogenetic networks I've just shown you. And denoting by N the number of leaves and by K the number of reticulation nodes. And again, we're talking about non-plane leaf-labeled networks. Remarkably, it was found that all of these types of networks, asymptotically, the number of these networks with N leaves and K reticulation nodes is equivalent, and it's equivalent to this expression. So I'm going to now show you the results that we did on the time-consistent gold trees. We're not just for completion, also working on general gold trees. So to do that, we'll first look at derivation of the generating function. So first, the bivariate generating function. So again, we denote by N the number of leaves. And here we are counting the number of golds by G. And we have the bivariate generating function. So a time-consistent gold tree can either be a leaf, or we can have a root with two main subtrees, which are themselves time-consistent gold trees, or we can have what we call a root gold, which is a gold that involves the root. And then we have the reticulation node, from which also comes a time-consistent gold tree. And because of the time consistency condition, we must have at least one node on each side of the reticulation node, which is not the root. And it can be, we can have up to any number of nodes on each side of the reticulation nodes. And from all of them, they have come from them subtrees, which are themselves time-consistent gold trees. And from this, we can get the bivariate generating function. Now, if we want the generating function with a specific fixed number of goals G, then we derivate this function with respect to UG time, substitute U with 0, and we get this expression for the generating function of leaf-labeled time-consistent goal trees with exactly G goals. And using induction and results and work we did on unlabeled time-consistent goal trees, we get the asymptotic approximation as n goes to infinity for this generating function, where C2G minus 1 is the 2G minus 1 Catalan number. And just substituting for one of the identities of the Catalan number, we get this approximation, again, for the generating function of leaf-labeled time-consistent goal trees with exactly G goals. So from this, we can, just to remind you that n is the number of leaves, G is the number of goals, and K is the number of articulation nodes. Using a transfer theorem, we get the asymptotic approximation for the number of leaf-labeled time-consistent goal trees with n leaves and exactly G goals, using also the Stirling approximation for n factorial. And because in goal trees, the number of goals is equivalent to the number of K reticulation nodes, then this is actually the asymptotic approximation as n goes to infinity of the number of leaf-labeled time-consistent goal trees with K reticulation nodes. And now we go back to these, to the approximation of all of these other more complex types of networks. And we see that the expressions are very similar. However, they're not identical. There are fewer goal trees than there are all of these a bit more complex phylogenetic networks. Also importantly, when K equals 0, we just go back, all of the network become rooted binary trees, and the expression are identical. And the same goes when K equals 1, then all of these are actually goal trees with one goal, and the expressions are also identical. And just again, these were all results as n goes to infinity. So just now to get the exact numbers of these time-consistent goal trees for small networks with the small number of leaves. So to calculate that, we used recursion, and here are the numbers. So these are probably known numbers of the rooted leaf-labeled binary trees, and these are also known numbers just with the one reticulation cycle. And all of these missing numbers are because to get G goals, we have to have at least 2G plus 1 leaves. So to summarize, we derived the generating function of leaf-labeled and time-consistent goal trees with G goals. And for that, we got the asymptotic approximation for the number of leaf-labeled time-consistent goal trees with n leaves and G goals or K reticulation nodes. And this is smaller than the approximation for all of these types of more complex phylogenetic networks, which are themselves equal asymptotically. And these are just acknowledgements, and thank you.